Here is our sixth conversation for Chapter 6, talking about collisions. We've talked about momentum and impulse. We briefly talked about bouncing, and you have been introduced to the idea of conservation of momentum. So let's see how this applies with collisions. Um, for collisions, we are looking at a system of the two objects that are colliding. So we are not we are only considering the forces that they exert on each other. And here's where your conservation of momentum comes in, is that the total momentum before the collision equals the total the total momentum after the collision. And there's your famous formula. And make a note of this. Anytime that we're talking about conservation, it's going to be a formula that looks like this, that is looking at the before and the after. Brush up on your algebra, because that's how you're going to solve problems like this. We can talk about a elastic collision, and that's when there's some bouncing, there's some rebounding, and the objects involved don't generate heat, they don't have a deformation. So when we get onto future chapters where we talk about the conservation of energy, when the collision is elastic, nothing else is happening except a change in direction and velocity. When it's an inelastic collision, then there is some energy being dissipated elsewhere. And when we talk about trains, we look at the fact that these couplings are a little bit loose, and that is by design. So that when these two train cars collide, the couplings will take some of the energy from the collision. So if it's an elastic collision, we've got a car moving, as an example, we've got a car moving at 10 meters per second, and it collides with another car that has a velocity of 0. And to make it simple, we'll say that they have the same mass. So the conservation of momentum is going to tell us that, first off, here's what we know, that the momentum before the collision is the same, the total momentum is the same before the collision and after the collision. So before the collision, we've got a mass moving at 10 kilometers an hour. That's the first car. The second car has a velocity of 0, so it doesn't even add to the momentum before. Okay. Afterwards, we've got double the mass and some unknown velocity. Oh, what they don't tell you in this problem is that these cars are going in the same direction. So when after the collision, when the mass is doubled, it's some new velocity, and when we do the algebra, our after collision velocity is 5 meters per second. Another easy way to look at it is that the velocity of the original car has gone down by half when its mass has doubled. Be able to work this out on paper and pencil. This is a really good example problem to just be able to do off the top of your head, and it will help you remember the relationships in momentums. All right, here's a question for you. I've got a couple freight cars. Same thing. We've got a freight car moving, and it's coming up at a freight car that's at rest. They're going to collide and couple together. So there will be a resultant velocity with the two cars going together. Compared to the initial speed of the red freight car, what will the speed of the coupled freight cars be? What will the speed be after they collide and connect? Now, just like the problem I told you to remember in your head, the mass has doubled, so the velocity has gone to half. And that's because the total mass before the impact, the total momentum before the impact is equal to the total momentum after the impact, because momentum is conserved.